course. We've been we started to cover this slide deck yesterday on the canonical New Keynesian model, which we're going to finalize today in our first lecture. Okay? As I said, the speed by which we are covering this slide deck is faster than the speed by which we will be going through the new material, coming later today. So what was the big takeaway so far from this slide deck? Well, the reason why there is this New Keynesian model, the reason why lots of the academic research community as well as central banks are working with a model that's called the so-called New Keynesian model is because it can address some of the empirical evidence that we reviewed yesterday. This is a plot that we discussed extensively yesterday that it shows and displays what are the empirical effects of a sudden change in the normal interest rate. So there is a sudden cut in the normal interest rate in the data, and empirical evidence suggests that in response to that, economic activity increases. So there's a rise in economic activity, and there's also a small but noticeable rise in inflation. And the New Keynesian model is a model that can account for this empirical evidence. So how does this model look like? Well, we discussed this at length yesterday, that there are three equations that can be derived that describe this model. There is a so-called Phillips curve, there is an IS curve, and then there is a Taylor curve. And this slide deck is designed to derive these three equations. And in these three equations, there is one shock that we're going to examine, which is this monetary policy shock. It's a deviation from a monetary policy interest rate rule. Okay? There is also a technology shock, but we're going to not spend too much time on that. Okay, so then the whole idea is that the crucial ingredient of the New Keynesian model is price decadence. If anybody ever asks you what's going on in this model, why does this model perform so differently than the business cycle model, it's because prices are sticky. We also discussed yesterday that the stickiness in prices in these models always comes together with a setup of monopolistic competition. Because if somebody has to set a price, even though that's going to be sticky, somebody has to have some market power to do so. So then the three building blocks in this model is the household part, there's the firm's part, and then this monetary policy part. And we finished the household part. And essentially, you can think about that the households have a standard dynamic optimization problem that you can break down into two parts. The first part is a so-called intratemporal decision. So it's a decision, it's a decision of intratemporal that gives rise to the demand for individual goods. And then there's the intertemporal decision that gives rise to the over time demand for goods. What is important, of course, is that in this model, right, there's a distinction between the consumption basket that derives utility and the purchases of the individual goods comprising that basket. All right, so then we reviewed that intratemporal decision, and when you do this intratemporal decision, that gives rise to this demand function for individual goods, or for varieties. Okay, so demand for variety J as a function of the relative price, of the demand elasticity, and of the level of overall economic activity. So that's the output, so to say, from the intratemporal household decision. The second step then was the intertemporal decision, and that intertemporal decision gives rise to two additional equations, which is, the first one is the intertemporal household consumption function, or the Euler equation. We learned that demand for consumption at the aggregate level is a function of, inter alia, the real interest rate. And we discussed that in detail yesterday, that when the real interest rate goes up, and when the real interest rate falls, then that increases consumption demand. The second equation that that results from this problem is the so-called labor supply equation. It's the optimal supply of labor as a function of the real wage and the wealth, the level of wealth that this household has, in a sense, in terms of measured in terms of consumption. Alright, so the household problem is very standard in the sense of giving rise to these two equations plus the demand for the variety of goods. We then went to the second block of this model yesterday. We started with that, and that pertains to firms. So what are firms doing in this economy? Well, firms are supplying goods. They are producing the consumption goods. They are demanding labor to produce, and they're setting prices. That's the overall setup what firms are doing. And then we familiarized ourselves with the environment. So output here is produced with the labor input and with an aggregate level of technology. So the number of tomatoes produced is a function of the number of hours worked put into the farming, to produce these tomatoes, and multiplied by a term that is representing aggregate technology, the efficiency by which this additional, by which the tomatoes can be produced. Okay. And then in terms of the market structure, each good J is produced by a monopolist. And so we have an infinite amount of goods J, and each good J is produced by a monopolist. There's exactly one producer of exactly a red tomato. And then there's another producer of a red tomato that has a shade of yellow. And then there is another producer of tomatoes that is a shade of green, and so forth. You can think about other examples, like if you think of wine, right? There is red wine from Italy and red wine from France, and I'm sure red wine from any other place you can dream of. These are all red wines, but they differ in terms of variety. Okay, so that gives rise to monopolistic competition because if one of these goods gets too expensive, consumers can shift away from red wine from Italy toward red wine from France, say, or from New Zealand. So that is something that's going to be important. Now, the most important part that we discussed also yesterday is that the degree of nominal rigidity is measured by a parameter called omega, which parameterizes the importance of so-called price adjustment costs. So there are costs of adjusting prices. When the price changes relative to yesterday, there are costs that are that the firm has to pay to change its price. If omega is equal to 0, then we are in the flexible price world, and if omega is positive, then we are in the so-called sticky price world. Now this is called Rothenberg price adjustment. Going back to Julio Rothenberg, who was a professor at Harvard University, who proposed this, and it is widely used. And as you will see, and you have already read, I hope, yesterday afternoon, the macroclimate paper. You have noticed that in the macroclimate paper that we're going to study, that exact Rothenberg specification is used, rather than another specification by which you can introduce nominal rigidity into the New Keynesian model, which is based on Calvo pricing. Calvo pricing is done. We have done that with Alexander Meyer-Hohle, for instance. Right? That's another way to introduce nominal rigidities. And interestingly, we had a discussion yesterday that up to a log linearization, up to first order approximation, you're going to get the same results, whether you use Rothenberg or Calvo for the aggregate. Okay? So for aggregate inflation, for aggregate output, and so forth. All right. Now then, the second to last slide that we covered in our last lecture was that the profit function of the firm now becomes an intertemporal problem, in the sense that the profits of the firm are its revenues minus its labor costs minus the adjustment costs. And then there is discounting at the household discount factor, and these profits, those profits are in dollars or in Vietnamese dong, right? These are nominal profits, and they're converted into utilities, into euros, by multiplying it with the household marginal utility of consumption. Okay, so D is the marginal utility of consumption that converts what is the worth of $1 in terms of utility. Now this is an intertemporal problem in the sense that the firms choose a price, but notice it's intertemporal because the price shows up with different time indices. there is PT plus I here, there is PT plus I here, but there is PT plus I minus 1 here. That's the reason why this is an intertemporal problem. Because your choice of the price today affects not only your revenues, but it also affects the price adjustment costs. And if you decide to increase your price today, that's going to increase your adjustment costs. But tomorrow, if you think about reducing your price, it's going to create another problem. It's going to create yet another price adjustment cost. So a firm price path that goes like this, if a firm decides to increase its price and then decreases its price, that invokes the adjustment cost twice. Right? On the upside, you have to pay price adjustment costs. So that's going to create price adjustment costs today. But then tomorrow, if you think, oh, now I want to cut my price as a firm, you're going to invoke another price adjustment cost. So you're going to have twice the adjustment costs. And that's why the firm intertemporally takes this into account and says, maybe it's not such a smart idea to increase my price today by that much and tomorrow by that much down. Maybe a little smaller adjustment is better because it's going to minimize the amount of adjustment costs. That's the whole idea why this becomes an intertemporal problem. So let me annotate this, right? That green here is important, that T minus 1. Now the firm then also understands that there are constraints. The first constraint is the production function, and the second constraint that the firm operates under is the demand function. And let me take out this yellow, this here, these arrows. I want to be a little more careful. So the firm maximizes its profits, understanding there's two constraints under which the firm operates. The first is the production function, and the second one is this demand function coming from the household sector. The firm manager understands if it chooses a very high price, it's going to have little demand for its products and vice versa. So then the way this goes is you're going to take the first equation and you're going to plug in that you're going to use that to substitute out for n. And that's, I was a little fast yesterday. So you're going to first substitute out for n, and then what you're going to do is you're going to take that demand function and you're going to plug that in everywhere. You're going to see the c. And that's the whole. That was the mention or the meaning of the arrows I tried to scribble out yesterday. So you're plugging in those two constraints, and then you take first order conditions with respect to the price indexes. And so that's what we have here, and we finish with this slide. Right? So after substitution, what you have is the profit function, is this expression, right? Where you can now think about this is the price minus marginal cost. We'll define this on another slide, but intuitively, this is price minus marginal cost. That's the margin. That's the margin that the firm has. And times the demand minus the adjustment costs. And then the appendix gives you the derivations from this equation in terms of first order conditions to this. And that's the optimal pricing rule. And so that's what the manager is working hard on to derive, and figuring out the optimal price that this firm has is a function of a lot of things. And that's called the optimal pricing rule. And we're going to work on this now, and it's going to yield the so-called Buchanan's and Phillips rule. It's going to be the first equation that this one has. Okay, so that's where we left off yesterday. Are there any questions that came up when you were reviewing the material in the afternoon? Is there anything that surfaced in terms of...
Alert from software update.
So that was a question from Google. Ming, please go ahead.
So can I ask, yesterday you mentioned that the third so-called role of the theta that appear in the price setting.
Yeah.
Can you give us a little bit of interpretation?
What the theta is? So the theta, let's go back here. Okay, so the theta, we can just look at that here. So the theta is the elasticity of demand. Let's write this down. So the theta is the elasticity of demand. Is the elasticity of demand for variety J. For variety J. So that means it's the sensitivity by which demand changes when the price of that demand changes. That's how you think about that. Okay? So literally looking at that equation, if the price of a variety goes up by 1%, the quantity by which this variety is demanded goes down by theta percent. So that's the idea. So numerically, what we're going to be using later on, we're going to set, for instance, theta equal to the number 6. So that's it's a standard calibration of the literature. So what does this number 6 mean? Well, the number 6 means that if the price or if the relative price of, say, tomatoes increases by 1%, the quantity of tomatoes demanded decreases by 6%. Okay, so that's the numerical interpretation that you would have to have. So that's the demand elasticity. Does this help? Is this, yeah?
Can I ask another
Oh,
question?
yeah.
Right. So for this kind of like price setting setup, because we have the Rothenberg pricing,
Yeah.
which is the quadratic. So
Yeah.
actually, firm prefer small adjustment.
That's right.
But
That's
then,
right.
like, I find a bit hard to comprehend because initially the whole idea is that we want to keep price linear and unit cost. Meaning firm doesn't want to adjust the price as frequently as possible, but
Mhm.
it is suggested that they want to do it as frequently as possible. So it is a bit hard for me to comprehend.
So in general, means there's different paradigms of introducing nominal unities in models. There are there are so-called time-dependent adjustment models and so-called state-dependent adjustment models. The state-dependent adjustment models are, for instance, models with menu costs, or in general, what's called SS adjustment type models. Okay, so that means firms prefer to keep their price unchanged for some time until it's optimal for the firm to change its price because it's eating too much into its profit. So it's a decision when and by how much to adjust prices. So that's the whole nature of so-called menu cost or state-dependent pricing models. Then there are the time-dependent adjustment models, and those are, for instance, Calvo pricing. There's a literature that shows that the Calvo pricing up to a first order is a good approximation to the menu cost models for small inflation rates. Okay? So the Calvo model is an approximation to the richer menu cost model. Why do people work with the Calvo model more than with menu cost models? Because menu cost models are very hard to solve. They are very challenging numerically to solve. They're very challenging to work with in larger models. And the time-dependent models are much easier to work with computational. Like for instance, I was working at the Federal Reserve. We had a New Keynesian model with 1,000 equations in 1,000 unknowns. It would be literally impossible to work with a menu cost model with such a big model. It's impossible, right? So often menu cost models, can be used for small models, but not for larger models used in central banks. Okay? So that's why the time-dependent models are very popular. Now, among the time-dependent models, you have Calvo and you have Rothenberg, and there's also others, but let's think about Calvo and Rothenberg. Now, up to a log linearization, Calvo and Rothenberg are exactly the same at the macro level. And you're right, and we discussed this yesterday also, that in Calvo, you have individual prices that look like this, right? A firm doesn't change its price until it exogenously can move its price, right? While in Rothenberg, firms can change their prices all the time. It's just the amount by which they change their prices differs. So the microeconomic implications of Calvo versus Rothenberg are different. Importantly, the macroeconomic implications mean. Okay, so if you go to our three equations, the macroeconomic implications of Calvo versus Rothenberg are exactly the same.
You still get the NKBC.
That's exactly the first equation, right? The New Keynesian Phillips curve is exactly identical in Rothenberg versus Calvo. So, And that's what we are trying to achieve here, because I mean, I grant your curiosity, but we are trying to explain macroeconomic facts here. You're trying, right? The new Keynesian model is a model that was designed in the first place to capture the macroeconomic effects, so the macroeconomic effects of interest rate change to the aggregate level of poverty, to the aggregate level of consumption, to the aggregate level of inflation. Now, I share your curiosity. You could say, okay, now let's go one level down and say, think about the micro implications, and then that opens a whole can of worms. Absolutely. But for our purposes, for understanding macro dynamics, this one is giving you exactly the same ideas. Now, I chose also this Rothenberg setup here because, as I said, in the macro climate model, they are using the Rothenberg setup. It turns out the Rothenberg setup is also much easier to use when you want to work with a so-called non-linear model. So if you do not want to log linearize the model, the Rothenberg is much easier to work with than the Campbell model. So that's I hope that helps to put it a little bit in perspective. Yeah? Okay. Any follow-up questions? Yeah?
I think it's really interesting that
Right.
you the quadratic functions to just for that, because like whether you just higher or lower, you still have the same positive cost for that.
Exactly. That's right. No? So this is like there are costs whether you cut your price or you increase your price. I mean, Julio Rothenberg, when he wrote this paper, he had a different idea in mind, and then it got adopted in this literature in the pricing sense. The first paper Julio Rothenberg wrote was about customer anger. No, seriously, it's not about that there's costs that firms have when they change their price, which firms have. When you go on your streets and when firms change their prices, they have to reprint some menus and blah blah blah. But Julio Rothenberg's first idea was no. If I have as a firm change my price, my customers are angry at me because that they hate keeping track of prices. When I want to buy my morning coffee, I always want to know. It's like automatic. I want to buy my morning coffee. I don't even want to think about what that costs because it always costs the same. And when a firm starts changing prices, I get angry. I say, oh, now I have to think about it. Is this too expensive? Shall I go to another store? So that's Julio Rothenberg's customer anger is actually the idea that is behind these adjustment costs. And then the New Keynesian literature figured, oh, wait a second, we can also use this for the cost of pricing prices, the cost of changing prices. It's a beautiful paper by Julio Rothenberg, right? So that when he wrote this customer anger paper.
And one has like, because I'm interested in the math, so I think like there was some kind of research about different functions.
Oh, yeah.
Because like when we use the quadratic functions, we will let it symmetric around the paths. So they treat it the same way. So it might not be really realistic.
That's a great question, Louis. So the idea is that this is symmetric, right? But you could think about, wait a second, you could think about it as a cubic, or there's asymmetry, that the costs of cutting prices are different than the cost of increasing prices, right? Maybe cost of increasing prices are larger than cost of cutting prices, right? You're shying away more customers when you're on the upslope than when you're on the downslope. I mean, the sky is literally the limit, there, and but of course, then once you introduce asymmetries, you cannot work with a log linear model. You cannot work with a linear model, right? Because in the linear model, once you log linearize around the steady state, everything is symmetric, up and down. So then you would need to work with a non-linear setting. But we will start doing this, later today and tomorrow and the day after tomorrow. We will work with non-linear models. But very nice, to think about this as asymmetric. All right. Other questions? And you guys are great. Yesterday was fantastic. That everybody spoke up and asked. I can encourage everyone to keep doing this. The learning outcome is going to be much better by, you being involved and asking every question that comes to your mind. So that's really good. Okay.
Also, give me some water first.
Oh, I see. Thank you very much. Thank you. That was great. Everyone grabs a water bottle. Okay, so what do we have here then? This is our optimal pricing equation, and admittedly that optimal pricing equation looks a little complicated, no? I mean, there's a constant in there, there's not time varying, then there's an expression here that, which has the real wage and technology in it, and then there is an expression that has the rate of inflation, and then it gets even worse, and there's another expression that has future expected inflation and an ugly ratio with exponents and all kinds of stuff in it. No? I mean, it's not the most intuitive expression to think of. So that's why I'm going to proceed now in 2 steps. And first what I'm going to do is, let's consider the case when omega is equal to 0. What is this model when you set omega equal to 0? Prices are flexible, exactly, right? When omega is equal to 0, prices are flexible. So that's a useful starting point. And when you notice, what you see is when you set omega equal to 0, oh, this term drops off. And then, oh, this term drops off as well. So it makes that optimal pricing equation much simpler. And so that's what we're going to do in the first case. So we're going to go and we're going to start with, the first case, the price when prices are flexible, so when we set that omega equal to 0. And then the optimal price setting equation boils down to this super simple equation. And I promise, Ivy, Alexa, everyone has seen this equation. Your first name is Oan, right?
Yeah.
Perfect. No, that's it. Oan? Okay, good. So I don't want to, Dean has it, everybody has it up, Juan has. Perfect. We have all the name tags up, but I promise I try to learn the name. So, anyways, right? Everyone in this classroom now has seen this equation. And maybe not that very equation, but the economics behind you have seen in your microeconomics classes. You go to your micro fundamentals classes in your masters or even in your bachelors, you have seen an equation like this. Now, maybe not exactly the same structure. So let me rewrite this equation so it gets closer to what you've seen earlier in your lives. So in the first place, let me define marginal costs. So marginal cost is the wage divided by the marginal part of labor. So the wage on the numerator and the marginal part of labor is ZT, right? Because the production function is linear, you differentiate that with respect to labor, marginal part of labor, that's Z. So that is, we can now go and we can substitute here the marginal cost that we just defined. Right? And then I can take that equation and put the price level on the left-hand side and the rest on the right-hand side. And that's what this famous equation is. That is the resulting equations coming from this little substitution. So what is this equation? With flexible prices, firms set a price PT as a function of their marginal cost times a ratio, theta over theta minus 1. Now let's do a little bit of a numerical example. Let's go back to the case that we discussed with Min. So let's set theta equal to 1.2. What is this theta over theta minus 1 numerically then? Well, then we're going to have 6 divided by 5, right? Which is 1.2. So, right, what I do here when theta is equal to 6, no, what am I doing here? I was too fast in my head. So let me be very careful. I don't want to, puzzle you guys. Okay, so if I set theta equal to 6, then theta over theta minus 1 is 6 divided by 6 minus 1. That is equal to 6 divided by 5. And that is equal to 1.2, right? So in other words, what this equation now says, a firm sets its price equal to 1.2 times marginal cost. That is the classic markup pricing equation. The firm sets its price as a markup over marginal cost. So if marginal costs are 100 Vietnamese dong for 1 tomato, then the firm sets a price of 120 Vietnamese dong. So that's what this markup pricing means. So in other words, this ratio theta over theta minus 1 is nothing else, and that's what's often abbreviated, is nothing else than just mu, the markup, the gross price markup. So let's write this down. So this is the gross price markup. So that's the gross price markup. Now, you notice that the markup, so the gross markup is 1.2, the net markup, of course, is 20%, right? The net markup that the firm has then is 20%. So what this means is that, the markup in this model is a function of theta too. So theta does many things. Theta is the elasticity of demand, right? But theta also affects the markup that firms have, or, put differently, the degree of monopoly power that a firm has. In general, the higher theta, the lower the markup. And vice versa, the lower theta, the higher the markup, right? So that's the key idea. If you drive theta to infinity, if you drive theta to really high numbers, then the gross markup approaches 1. So notice that when theta goes to 1, then the markup goes to 1. Meaning, then you're back to perfect competition, that the price is equal to the marginal cost. So in other words, when theta goes to, what am I doing? I'm very sorry. What am I doing here? Let me just, I think I'm trying to be, okay, so if theta goes to infinity, then the markup goes to 1. So meaning that's really, that's perfect competition. So that is perfect competition. Perfect competition. That means that we have perfect competition. Prices are equal to marginal cost. Intuitively, if theta is infinity, then if the firm changes its price by a very small amount, the firm will not sell any quantity because the price is not equal to the perfect competition price. Okay. And then conversely, if theta goes the other way, if theta goes to 1, then the markup becomes infinite. The firm has infinite market power, and that's exactly what we need in this model. That monopolistic competition, the degree of the demand elasticity implies things for the markup, and that controls by how much firms are exposed to competition from their competitors. All right. Any questions on this? So everybody has seen this in your micro classes, one way or the other, right? We've just derived the standard microeconomics result. All right. Now, when we go one step further, with this in mind, we can then derive what the literature calls potential output, which is the level of output with flexible prices. Now, when all prices are flexible, we can already calculate in this model how does output respond to changes in the economy. And what we need for that is we need 3 little equations. We need the optimal price setting equation. We need the labor supply equation from the households. And we need the aggregate production. And when you combine those 3 equations, you're going to get this equation down here. Let me tell you how you do this. So the first thing you do is you take the optimal, you're going to take the production function, and then you use that to substitute out for n. So that's the first substitution you do. Take that n, plug that in there, and then you take this equation, and you're using the real wage to plug that into there. And then the resulting equation, you log linearize. You do a first order Taylor series expansion, and then you're going to get this result. So I've written all of this out in the appendix for you guys. So that's a little homework for the afternoon. Try to get to these steps. So long story short, you take 3 equations from the model, you do substitutions, and then you log linearize, and then you're going to get that. So what is what is this YT F head meaning? Well, it's the natural logarithm of YTF divided by its steady state, where F here means flexible. Okay, that's the superscript F here means it's the flexible price output. So this is output with flexible prices. And what you learn is that, in these derivations is that, in this model with flexible prices, potential output is a function of model parameters, but importantly, it's a function of technology. So ZT head is technology. It's the percent deviations of technology from its trend, from its steady state. So ZT head is equal to the natural logarithm of ZT over Z bar. So that's nothing else than just the RBC world, right? Where output depends only on fluctuations of technology. When technology goes up, output goes up. When technology falls, output falls. So that's the only, so to say, a driver, in this model with flexible prices. Notice that monetary policy does not affect flex price output. Right? Monetary policy is not changing flex price output, not by assumption, but as a model result. You just arrive as an equation that maps an exogenous variable, technology, which is exogenous to this economy, to an endogenous model, a variable, which is output. And you see in that mapping, right, there's no monetary policy showing. So with flexible prices, output is unaffected by monetary policy. That's already a result to keep in mind. Now, why am I spending time on this? Well, as we're going to see, the amount of flexible price output fluctuations is a useful benchmark later on. It's something that the central bank may want to keep in mind when designing central monetary policy. Any questions on this one?
Can I ask something which may seem like a naive, but then usually how can we decide which level is the steady state?
Okay, so the steady state is when you take these three equations, you are taking away the subscripts and you solve for the steady state. So the steady state is you take these three equations, you drop the time subscripts, and then you solve for the allocations for the steady state. So in other words, there will be an equation in the steady state that maps your output in steady state as a function of model parameters and the level of technology. So when the level of technology in steady state is high, your steady state output will be higher. If your level of technology is low, your steady state output will be low. So that's sort of the underlying here. So this Y bar, there will be an equation that will look like similar to this, not exactly, but will be looking similar like this, that maps steady state output to steady state of technology. Try to work this out, it's not difficult. Do the same steps that I do here, and then before you log linearize, you're just going to drop the time subscripts and solve for the steady state. By the way, does everybody know how to log linearize? Who doesn't know how to log linearize?
Actually, in our reference talk, Professor Alexander also the log line.
Yeah, perfect. So if you're struggling, go back to Alexander Mayer-Go. This is class he did. I know that he does that in his classes, the log linearization. But if you're struggling with this, you maybe just want to go and think about this is a first order Taylor series expansion. So this is a first order Taylor series expansion. Just approximate every equilibrium equation with a first order Taylor series expansion. Great, thank you. Okay, good. So we have all that under control. Now let's go back then to the general case. Okay? Let's go back to the sticky price case. So that is now when omega is going to be larger than 0. So that is our second case. And in that case, we have to go back to our original function, our optimal price setting rule. So this is the optimal price setting rule. And I did one little extra substitution here. So if you go back to equation number 3, right, it had this W over PT times ZT in it. And I'm going to define now real marginal costs. So this is nominal marginal cost divided by the price level. So when you write this down, so real marginal cost is nominal marginal cost. It's the dollar or Vietnamese dong marginal cost divided by the price level. And then what you're going to do is you're going to take that equation and you log linearize that equation. And that's like, right, you log linearize that equation around the steady state, and the steady state around which this is log linearized is aggregate inflation is 0, so gross inflation is 1. And in steady state, marginal cost is a function of the ratio of the demand elasticity. And then as a result, when you log linearize this equation, this looks ugly. This is like, doesn't look nice. No, it's not something that you would think of dreaming about. And when you log linearize it, it looks like this equation all of a sudden. It becomes this equation, which is a famous equation. Right? So this equation is what's called the Lucasian-Phillips curve. Here we go. This is the first equation from the 3 equations we discussed with the one little thing. So what does this equation tell us intuitively? Well, the rate of inflation in our economy, according to the model, is a function of the expected rate of inflation. So it's the expectation about future inflation, and as a function of firms' marginal cost. And then there's parameters. There is the slope of the Phillips curve, and then there is beta, which is the discount factor by households. So this is what many of the literature calls an expectations augmented Phillips curve. Let's go in steps. What's the intuition for, right, when marginal costs are changing? So suppose marginal cost is changing. Suppose marginal costs are high. So there's a terrible. So let's first think, when can marginal costs be high? Well, for instance, suppose there's a terrible typhoon hitting Vietnam, so destroying lots of the technology available to grow tomatoes, say. So when Z is low, when you have a bad technology shock, then marginal costs are going up. So for every tomato to produce, right, so let's go through this. When you want to produce tomatoes and there is a bad technology shock, and you can think about bad weather, flooding, but also electricity prices going up, anything that hampers firms' productivity that maps into this. And what you see is ceteris paribus, when Z goes down, marginal costs go up. So each unit produced is more expensive. And according to the theory here is that when marginal costs then go up, right, ceteris paribus, inflation goes up. Can somebody think about the channel by which this happens in this model? So why is when firms have higher costs, why is inflation going up in this economy? It's a simple question. Maybe too simple for you folks.
Yeah, showing supply chain.
Exactly.
I think supply chain.
That's right. So when firms have higher costs, their supply is disrupted. They're going to pass on these higher costs onto their firms' customers. If it's twice as expensive to produce tomatoes now, then at the marketplace, the customers have to pay higher prices because the firm, is going to charge higher prices as a result. So that's going to produce more inflation. Okay, so that's the standard firm cost channel. Then there is another expression here, which is expected inflation. And so suppose firms expect inflation to go up tomorrow. So suppose they have learned there is a war in Iran, and that oil prices are, under stress, under pressure, and they expect oil prices to be higher tomorrow. Because at the Strait of Hormuz, you can get oil tankers across, and everybody expects higher oil prices tomorrow. What is the mechanism when you have higher oil price expectations tomorrow, and thereby higher inflation expectations, through the lens of the model? Why does that increase inflation already today? What's that? You consume, ceteris paribus, that's right. If everything else is unchanged, if you expect higher prices tomorrow, you will consume more today, right? You will go and say, oh, now I have to buy 10 liters of gasoline because tomorrow is going to be more expensive than today too. Fantastic. And because that's going to create more demand, then you're going to get more inflation. That's exactly one channel by which this works. There's another channel by which this works. Even if demand doesn't change at all, I mean, it's in general equilibrium, it's great that you think about general equilibrium, but even absent general equilibrium, why would a manager, if the manager knows it's going to be more inflation tomorrow, why would a manager decide, even absent the demand effects, to increase its prices?
Reduce the.
Go in that second thought. It's costly, right? So in other words, if they do nothing today, but they have to increase their prices a lot tomorrow, then that cost will hit. And because it's quadratic, a large price hike tomorrow would be very costly in terms of price adjustment costs. So the firm prefers to change its prices a little in both periods. That's why already raising prices today, so you have a little bit of adjustment cost today, and then you're going to keep raising your prices tomorrow. Two little price hikes are less expensive than one giant price hike. That's the idea. Okay. So we're going back to your idea on this, adjustment costs. When you have higher inflation expectations, that's going to feed into more higher prices already today because of this anticipation effect of the price adjustment costs. And then two is absolutely spot on, and there's an additional layer of additional demand that's also going to crank up inflation. You guys are great, fantastic. All right, good. So we have nailed that. We understand this Newton-Phillips curve. Are there any questions? Further questions? Now, this is a special thing for Min, right? This is the slope of the Phillips curve with Rothenberg pricing. When you do couple pricing, you get a coefficient that has other parameters in here. But there's also just one coefficient. And you can show numerically this coefficient can be identical to the couple coefficient. So you go to your other classes, the only difference of this equation with Calvo is that this coefficient looks different. That's just a number. Alright, good. So then, why is this called the New Keynesian-Phillips curve? We have discussed this, read about this, of course, before, because it's entirely microfounded. It comes from explicit optimization problems. This is microeconomics, right? We have a household decision-making problem, we have a firm decision-making problem, and as a result, we're going to get a microfounded, New Keynesian-Phillips curve. And then we see that the sensitivity by which changes in marginal cost affect inflation is controlled by this coefficient here, right? So for instance, when omega, the stickiness of prices, if omega is high, so suppose omega is high, right? So supposing omega increases, you think about when omega increases, what's going to happen with this ratio? Well, obviously this ratio is going to fall. So any change in marginal costs are going to be less inflationary. So in other words, the more costly it becomes for a firm to change its prices, the less inflation you're going to see as a result. So that's a standard effect. So that's the first interpretation. And then the second interpretation is a little more subtle, but it's also important to be aware of. Namely that this New Keynesian-Phillips curve is strongly forward-looking. That's the expectations channel. It looks like inflation is a function of inflation expectations and marginal cost today. But you can take this equation and do iterative substitutions, and you're going to be able to rewrite the equation like this, where inflation is a function of current and future expected marginal costs. Let me show you how you can do that. You're going to take equation number 5, and you're going to write down the same equation one period ahead. So you're going to write this as pi t plus 1 head with an et in front. You're just going to lead that equation by one period. So you're going to have beta et of pi t plus 2 head plus theta minus 1 over omega mct plus 1 head, and then with an et, of course. So just move that equation one period forward, conditional on today's information set, et. And then what you do is you do repeated substitutions. You're going to take that and you're going to plug that in here. You're going to substitute out for pi t plus 1. And then what you're going to do is you're going to keep doing that over and over again. So you're going to write down an equation for et of pi t plus 2 head is equal to beta et of pi t plus 3 head plus theta minus 1 over omega et of mct plus 2 head. And then you're going to plug that in here. So you keep always substituting out the expected inflation term over and over and over again. And then what you're going to get as a result, you're going to get that equation. So you're literally getting rid of the expected inflation by substituting and substituting and substituting over and over. And as a result, you're going to get that little equation here, which is a very powerful equation. So that equation says the rate of inflation that we observe today in our economy is a function of the slope parameter, but more importantly, the present discounted sum of today's and future marginal costs. So the entire rate of inflation that we see today, so how much this bottle of water's prices changed from yesterday to today at the aggregate level, price level, is a function of today's marginal cost. So how costly it is for firms to produce today, but then also tomorrow, the day after tomorrow, the day after tomorrow, and so forth. So again, having this idea of firms look forward in their pricing decisions because of the adjustment costs that they want to try to minimize. Of course, they're not only trying to minimize adjustment costs, they're maximizing profits, but taking into account that changes in their prices is going to generate adjustment costs, and that's going to become an important factor. Okay. Any questions on this? All right. So then let's do one more step. If your eye is sharp, you should say, okay, Matthias, equation 4 is kind of interesting, but it looks a little different than the equation I gave you when we wrote down the 3 equations, right? So it looks a little different. I mean, this looks the same, but this term looks a little different. So let me be clear what I'm talking about here. So we go to our 3 equations that we started out and say we wanted to write those equations. Right? And if your eye is sharp, you notice that this is looking a little different than what we have to write so far. So I owe you one more step that is, giving you that, object here. And that's super simple to do because essentially what we want to do is we want to relate the Phillips curve that we derived so far to an object that's in the literature called the so-called output gap. So the first thing is that the object that we had on the earlier slide had this xt. So what is the xt? Well, the xt is the log difference of output from its flexible price. It's called the output gap. It's a measure of resource utilization in the economy. So we can have situations when actual output, so output with sticky prices, is larger than output with flexible prices. So when the output gap is positive, when this thing is a positive number, then that means sticky price output exceeds flexible price output. The output gap can also be negative when sticky price output is smaller than flexible price output. So that can all happen. Go ahead.
Sorry, Professor, don't mind if I ask, how can we relate the potential output to the output where the price is flexible? How do I get that connection?
Okay, so we defined it this way, right? So we define flexible output. Flex price output is the level of output, the definition, it's the level of output when all prices are flexible. So this is so think about this as it's a hypothetical economy. It's not the economy we're living in. We're living in an economy with sticky prices, right? So this is like a dream world, right? This is like how would the Vietnamese economy look like when all prices would be flexible? So it's a hypothetical concept. It's like a parallel world. We cannot observe that. I mean, we cannot observe it, let's put it like this. So that's how, and the superscript f is just, it defines that level of output. It says, you know, when you take those three equations, which are only valid with flexible prices, the resulting level of output, we define, or we denote by yf. Now, so that's where this flexible price output comes from. Going back to the definition of the output gap now is defined as the difference between the level of output in the actual Vietnamese economy with sticky prices compared to the level of output with flexible prices. Now you're saying, wait a second, you know, I'm comparing my economy with a hypothetical economy. What should that be good for? Well, from a central bank's perspective, you can think about whenever there are shocks hitting the economy, when there's a technology shock that hits the economy, it's going to hit this economy, it's going to hit the Vietnamese economy, but it's also going to hit this economy, the flexible price economy. And what you can show is that the flexible price economy gives you the efficient adjustment of the economy to changes, to shocks. So YF is efficient. This is the welfare maximizing, fluctuations that we have in the economy. So in other words, you know, when there's a technology shock hitting, YF gives us what's the optimal response in terms of how would the citizens of Vietnam be most happy. And that's what goes into YF. It's when we defined or when we worked out YF, let's go back here, that you can show that this flexible price or potential output, right, is nearly efficient in the sense that it is. What's that?
So the flexible price is like the baseline price.
That's right. And you can show that consumer welfare or social welfare is maximal when prices are flexible. Okay? So with flexible prices, welfare is maximal. So in other words, people in Vietnam would be more happy living in a flexible price economy than in a sticky price economy. So that's why this is a useful benchmark in the sense of, you know, a welfare maximizing level of output that you could attain. So in other words, it's like, it's welfare maximizing, write this down. It's welfare maximizing. Any level different from YF is not welfare maximizing. Alright, so then in terms of an output gap, the output gap is a measure, it's a measure of the inefficiency by which the economy works. So when output is above potential output, right, the economy is booming, the economy is not necessarily booming, but if output is larger than or exceeds potential output, you know, the output gap is positive, and you know, vice versa, when output is smaller than potential output, the output gap is negative. And what we're going to see later on, the central bank can try, can ask, is there a way for a central bank to make this YT equal to YTF? In other words, if you know the efficient response of the Vietnamese economy, can the central bank design a monetary policy via its interest rate so that the Vietnamese actual economy has an allocation in terms of GDP that is identical to the efficient level of output in this economy. So that's the idea. So this is hypothetical, this is welfare maximizing. We cannot live in that world. But can the central bank make our world in which we actually live look like the efficient level of the efficient economy? That's the key idea. That's the key question. So this output gap measures, so to say, that. Now maybe let me ask you intuitively, how can we think about, suppose there is a technology shock hitting, and that moves potential output up by 1%. And in the actual economy, potential output maybe is going up by more or less than this 1%. Maybe it's going up by more. Let's fix that as an example. Right? So efficient output goes up by 1%, and actual output goes up by 2%. Say. Suppose that may happen. How is it possible that, you know, when technology increases, that potential output goes up, that actual output can go beyond the flexible price output? How is this, you know, physically possible? In technology goes up by 1%, how can you produce more than just that 1%? What must happen in this economy? Who is producing this output? I'm looking for a buzzword here, which is called overtime work. People can temporarily work overtime. So when there are changes in the economy, if you ever wonder, so how can you get potential output to, the output gap to be positive? Suppose it's an even easier example. Maybe that example is going to be easier for you guys. Suppose YF is constant. YF doesn't move, but actual output goes up. The only way when that can happen is that when people in Vietnam work overtime. And then likewise, when the opposite happens, when you have a negative output gap, and that means people work less than their typical 8-hour or 12-hour workday. So in other words, it's the amount of over and under work time, in a sense, that gives rise to this change in the output gap. Okay. Just hold on just a little bit. It's a little hot today, isn't it? Well, harder than yesterday, I feel like it. All right. So now let's maybe cut through the chase here. How can we now relate these two things? What I'm going to show you is that the Phillips curve that we have derived here, right, so far, can be rewritten in terms of the output gap like this. So there's a very tight mapping between the marginal cost term and the expression that I have here. And now with this little substitution, you're going to be able to rewrite your Phillips curve like this, where there is now an xt in here. So how does this work? Well, you have to do a little bit of math. And the math is like this. You're going to have the definition of the real marginal cost. You have the labor supply equation, and you have the aggregate production function, or the resource equation. So notice that, in difference to the equations before we had the flexible price, optimal price level. Now we just have real marginal cost. And you do the same substitutions as before. So you take the output and solve for n and plug in for n there. And then you take the real wage and you plug in for the real wage there. And then you log linearize again. You log linearize, and the appendix shows that. And what you're going to get as a result is you're going to get that equation. In other words, you have these three equations. You substitute for n, you substitute for the real wage, and as a result you get that equation logged into the term. Very straightforward, 2 lines of math. And then you realize, well, we have an equation for potential output that maps to ZT. And so the potential output equation, or the flexible price output equation that we derived earlier, was 1 plus eta, sigma plus eta, ZT head, right? So we derived that equation like a couple of slides ago. And now we just take that Z and plug that in there. So we're going to take that Z and it goes in here. And then as a result, you're going to get that equation. So you will be able to write marginal cost as a coefficient times the difference of output minus fixed price output. And there we go. That's the output gap. There's a very tight mapping between marginal cost and the output gap. So we can write this explicitly, that the marginal cost is nothing else than just a function of the output gap. So in other words, whether you write the Phillips curve, right, and then you're going to take this marginal cost expression and you're going to plug that into the original Phillips curve that we derived, and as a result you will be able to rewrite it like this. Very straightforward, little bit of math. And now we have the Phillips curve as a function of expected inflation and the output gap. So if the output gap is positive, if actual output exceeds the efficient level of output, then you're going to get inflation. If the output gap is negative, in other words, if the output gap falls, then actual inflation is going to be less than in the efficient level. So that's a measure of resource efficiency. Now, in this economy now, what's of course important is by how much inflation increases, depends on this slope here that is equal to, or defined to be equal to, the parameter kappa that we have on the other slides. Okay, so it's a parameter that is comprised of four model parameters: the demand elasticity, the degree of price stickiness, the curvature in the utility function for labor, and the curvature of the utility function for consumption. Of course, all these parameters determine for a given change in the output gap. So if the output gap goes up by 1 percentage point, these coefficients determine by how much inflation is going to change. So in other words, what we'll see is, for instance, that if you think about this parameter eta here, eta measures the convexity in the disutility of labor. Go back to the household function, the household problem. So this is the household problem that we discussed. So eta, for instance, is a coefficient in the disutility of labor. The higher eta, the more curved is the disutility. So if eta is 1, then you have quadratic disutility. If eta is 2, then you have cubic disutility. So it gets more and more curved. So what does this mean? People really hate to work the higher eta. When eta is large, people really hate to work. Every additional hour is going to make them feel miserable. That's how you can think about what eta does. Now guess what happens if your boss comes into your office and says, you know what? I ask you to stay 2 hours longer today to do 2 hours of overtime. So rather than working like 8 or 10 hours, you need to work for 12 hours today. When your eta is high, you really hate that. You say, this is unbearable. And then you're going to ask your boss, well, I'm going to work overtime, but are you going to compensate me for that in a way or not? Okay, and the way this typically works is that people get extra compensation for overtime work. I don't know whether that's actually true in Vietnam, but say when you're in Germany or in the US, overtime work, you're going to get a premium. You're going to get some extra on your hourly wage. So how is this here in Vietnam? When you work overtime, you also get paid more, depending on, I take it on the occupation that you have, or the sometimes. Okay. You see, but sometimes it's enough. If it's happening for some jobs and not for others, then the aggregate of those there will be some extra overtime work compensation at the aggregate level on the average. Right? And that's all embedded now in this Phillips curve, right? If we go back to our Phillips curve equation, that is the higher eta, for instance, as an example, for a given output gap is going to produce more inflation. The intuition is that when people demand more higher wages, right, because of their eta being high, they dislike to work, that higher wage is going to morph into marginal cost that's going to increase inflation. So let's maybe write this down. So if eta is, for instance, higher, then we have that a given change in the economy is going to increase the wage. And with that increase in the wage, it's going to increase marginal cost, right? And that increase in marginal cost is going to increase inflation. That's the basic idea in this model. Everything goes through this marginal cost curve, on the interaction between changes in the economy to marginal cost. If you understand all that, you understand 99% of the new 90%, I should say, not 99, 90%. This is really the core of the new Keynesian model. We could stop here and could move on to the macro-quantum paper. You will see in many papers that in the new Keynesian literature that they have a very similar setup. Sometimes a little change here, sometimes a little change there, but the lion's share of papers has this type of setup. The rest could change, but now, given that I promised we're going to derive the 3 equations, there's 2 equations left over, but those will be like a walk in the park compared to deriving this new Keynesian. So how do we do this? Well, first of all, let's maybe collect what type of equations do we have, and is there an equation that we haven't used yet? So we have the Phillips curve, for instance, we haven't made use of the Euler equation yet. That's the equation we haven't touched, right? We use the labor supply equation, and that's the general equilibrium idea, right, in this model. I hope you realize that we use the labor supply equation in the derivation of the Lucasian Phillips curve. So I hope you realize that, right? We have made use, for instance, of this equation now multiple times. So that's already imposes equilibrium in the labor market in the sense that labor demand equals labor supply. We have made use of that. But the one equation that we haven't touched yet is the Euler equation. That we didn't dare touching yet. So we're going to be, and so that's one equation we have to do. And then, when you look closely, we also haven't really talked about R. What the central bank is doing, how the central bank is following like a strategy to policy. All right. So we have to work a little bit on that. And the next is we're going to work on this one. And it's super simple, folks. I mean, it's no magic at all. The whole idea is that when you take that equation and you log linearize it, it's going to look like this. So the Euler equation, once you log linearize it, it becomes this equation. Now there's one additional little assumption is that in this model, y is equal to c. So this is a closed economy, there's no trade, and there's no physical capital, there's no investment. That's why consumption is equal to output. So if you have capital, that equation is going to look a little different. If you have trade, that equation is going to look a little different. But given our closed economy, when output is equal to consumption, log linearizing the Euler equation gets you like this. So you can already start seeing how this starts to look like the IS curve. Right? A little bit. I mean, that's like output is a function of expected output minus the real rate. But when you look closely at that second equation that I gave you, it didn't have yt's in there, but it had xt's in there, right? So now we need to massage that equation a little bit to get it into x. You have to put in, we have to convert these y's into x's. And that's what we do in the second step here. In particular, what we do is we do an old trick in an old math trick, right? In particular, what we're going to do is we're going to add and subtract terms on the left and right hand side of this equation. So on the left hand side, you're going to add and subtract potential output. Don't change the equation, right? It's just adding and subtracting. And then likewise, on the right hand side, we're adding and subtracting potential output in condition expectations one period ahead. And now comes a little bit of magic, because now what you can do is you can see, oh, wait a second, there's a friend here looking our way, right? There's yt minus yf. Well, that's exactly the definition of the output then. So, this minus this is going to be exactly xt. And then this minus that is xt plus 1. So then this minus that is xt plus 1. And we have our real interest rate term. But then of course we must not forget that there's somebody over here that we haven't used yet, and then there's somebody here. So I'll just write down here. Okay, that equation in the literature is called that new IS curve. The new investment and savings curve. So IS always stands for investment and savings. Right? It tells you nothing else than just, are you going to invest in these bonds, or are you going to consume? Your investment choice is a mirror image of your consumption choice. So if you decide to increase your investment or increase your savings, well then, for a given amount of output or income, you decrease your consumption, and then vice versa. When you decrease your savings, you're going to increase your consumption, right? So that's basically always one is the flip side of the other, and it's the investment savings curve, that has gotten this name. Let me copy this equation to the next slide. And then what I want is, again, the devil is always in the detail, right? The second equation on this, three equations that I gave you didn't have this YTF. Back there. Make sure everybody's on board. Okay, so this, we want to derive that second equation now. And look, there's a ZT here with some alpha coefficient. And it doesn't have the YT minus YTF plus 1, right? That's not there. So we have one more step to go. And that's what we want to do together here. So we want to kind of convert this into technology. That's the idea. So do that. Let's do that together. And what you can, again, show is that you can convert this difference in potential output into just a ZT. It almost looks a little bit like magic the first time you see it. Well, oh, wait a second, there's an ET of YT plus 1 minus YTF. How the heck is this going to map into this little ZT here? Well, I'm going to show you. First thing to realize is, again, let's write down the definition of potential output. So YTF head is equal to 1 plus eta over sigma plus eta ZT head, right? So that is an equation that we have made use of multiple times. And let's, in addition, as we have done that, or it's custom to assume, let's assume that technology follows an AR1 process, like in the real business cycle model. It's an autoregressive exogenous process that technology is a function of its own lag plus an IID, a non-distributed random variable. So epsilon z is IID, standard normally distributed with a 0 mean and some variance sigma squared. So this epsilon fluctuates with mean 0 and some variance. Those two assumptions, that assumption on an AR1 plus the definition of the potential output is going to give us the mapping from here to there. Let's put that in steps. The first one is we're going to use this together with that to replace this YTF plus 1 by this expression. So this is nothing else than just our definition of potential output leaded one period. If you lead that by one period, so that's YT plus 1F, it is ET of CT plus 1. It's exactly this. And then this is just that. So there's nothing else, just plugging in the YTF. And then the second line is realizing that the conditional expectation of ZT plus 1 is just rho Z times ZT. So that second step is that ET of ZT plus 1 is nothing else than just rho Z ZT hat. That's that step from here to there. Notice that when we evaluate the expectation, ET of ZT plus 1 is just rho Z because it's an AR1 process. Because of the AR1 process, the conditional expectation of a random variable, because this has mean 0, right? This has mean 0. The conditional expectation is just rho times the capacity function. Okay, so then we can factor the ZT, and then it's going to give us this, where alpha is just a parameter, has a negative sign. That's not too much of a burden. It's just a collection of parameters. Excellent. So then we can take that and plug that into our IS curve, where we have now replaced that difference in potential output by this Z. And then last but not least, we have the Phillips curve. And this gives us the famous New model. In other words, there is the Phillips curve and the IS curve. Notice that this is entirely microfounded. In the 1960s and the 1970s, the way macroeconomics was done then was by people sitting down, maybe I'm exaggerating, but they were sitting in an armchair, and they were thinking, okay, how does the world work? Let me think. So I think inflation is a function of, must depend on this, and must depend on this. I'm not making this like in a disrespectful way. These are really esteemed and renowned economists. But in the 1960s and 1970s often, the way macro was done then, people wrote down ad hoc equations. They wrote ad hoc Phillips curves. They said inflation is a function of, say, the unemployment rate by some drug. And it's a function of this. And demand is a, looks like, so they assume ad hoc equations based on experience, sometimes based on empirical analysis, running regressions. And I mean to say this in a respectful way, right? That's how it was done in the 60s and 70s. Here, everything follows from first principles. Follows from utility maximization, follows from profit maximization. So there's no ad hocness. And that's the first big difference between those two very different approaches. And you can still, even though it's general equilibrium, you can still give names to these equations. So AS in many papers stands for aggregate supply, and AD for aggregate demand. And some of the successes of this model, right? I mean, this model, essentially this model, is one of the mainstream models these days in central banks and policymaking institutions and in academia. It is really, you go to any central bank in many countries that you will see people work with a version of these equations. I used to work at the European Central Bank, I used to work at the Riksbank, at the Swedish Central Bank, at the Bundesbank, I used to work at the Federal Reserve, and they're all using variants of this equation. Sometimes more complicated, more detailed, so you can put in commercial banks and shadow banks and investment and trade and, I mean, you name it. As I told you when I was working at the Federal Reserve, the model that we were operating there was a multi-country model with financial measures and fiscal policy and everything you can think of, and at the end, the version of the model that we used to brief the governors had 1,000 equations and 1,000 unknowns. Now that model had a lot of elements in it, of course, right? But at the end of the day, if you were to boil that model down, you say, okay, let's get rid of capital, let's get rid of banks, let's get rid of trade, you will arrive at those two equations, even in those super complicated models. So it is a very powerful and widespreadly used model. Now this model has not an interesting financial sector in it, and has come under quite some critique in the financial crisis. Because this model, as we write it down here, has really nothing to say about financial matters. So financial crisis is something that's absent from this model. The beauty of this model is it is so versatile that it can be extended to enrich it by a very fancy financial sector. You can enrich it into a fancy other sectors. You can have labor markets that are more interesting, the heterogeneity of firms and households. It's very versatile, if you like. And maybe, I mean, it's a little bit of shameless self-advertisement. I don't know whether I should do that, but let's try anyways. If you go to my personal website, so if you go to my personal website, that's on Google, right? So I have this Google website, matthiastrabant.com, and if you go to my research, go on the research tab, and then you go on, you go on that research tab, and then there's a paper that is titled, exactly. Let's see, there we go. So I wrote a paper together with Larry Cristiano and Murray Eichenbaum from Northwestern University titled On DSGE Models. If you click on that link, or if you click on that link, you're going to get that paper. So what does that paper do? It basically gives you a description of the RBC model, and then the New Keynesian baseline model that we derived, and then describes how did the profession work on changing that model to account for the things that happened in the financial crisis. And you're going to learn that putting in shadow banks and so forth is what the literature has done in order to enrich this model, and became, that's the leading framework still with, now with fancy, financial lines. So on DST points. Well then, after, the financial crisis was over, it just so happened that we were living in a world that another big crisis came our way. Can you remember what that crisis was? So the financial crisis was 2007, 2008. You were very young at that time. What's that? The Eurozone crisis. There was another crisis in 2012. Yeah, but then roll time a little forward. What other big crisis were we in now? We're in a global crisis. What was that? The COVID-19, right? We had the COVID-19 pandemic and the ensuing recession, right? In 2020, we had this global pandemic starting, and then many economies went into a recession in 2020, 2021, and so forth. Now, in the New Keynesian model that we discussed so far, right? Is there any pandemic there? Nothing, right? So you would think, well, it's not a useful model to think about pandemics. No? Well, be careful. Same thing goes as with this model having no interesting financial sector. You can augment this model to include an interesting financial sector, but you can also augment this model to include explicitly epidemic dynamics. So you can put in a virus into this model that spreads through the population. And you can then track, okay, what happens here as a consequence of a virus. So that's what I did with other co-authors, since we are in self-advertisement. So I wrote this paper together with Marty Eichenbaum and Sergio Ravello titled The Macroeconomics of Epidemics, where we show how to put in explicit epidemics into an RBC model, and then in another paper titled The Epidemics in the New Keynesian Model, we augment this model with an epidemic sector. And then we looked at what is the two-way interaction between the epidemic and the macroeconomy. When the virus spreads, people are precautioning, they're not going to the shopping center as much as before, that's going to slow down demand. There are people going to take measures at the workplace to not spread the virus, so that's going to reduce productivity, and that has implications for the macroeconomy. We showed that in this paper that when the virus kind of is raging through the population, the economy goes into recession. And we looked at what does the central bank have to do in response and da 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 da. So you can augment the model by that. So long story short, why am I giving this longer speech here? This model is very famous in the sense of being able to, be augmented to current circumstances. Right now, I have many former colleagues at central banks that work with this model and think about what are the macroeconomic effects of tariffs. Thinking about the US imposing tariffs, you can put in fiscal policy and tariffs in this model and think about what happens to the rate of inflation as a response to changes in tariffs. So one reason, that's a big question that students always have, so why is this the mainstream model in so many institutions? One reason is because it's a very versatile model that can be adapted to many things happening. And so that's something to keep in mind. Are there any questions? I think it's time for a break, if I'm not mistaken, right?
Yeah.
Okay, so why don't we have a 15-minute break and we reconvene at 11 a.m.? Would that be a good time? Yeah? Okay. So then enjoy the break, and I'll look forward to